All right, today we're going to be looking at something called matrix equations. We're going to be looking a little more in detail to some of the stuff we've been doing. So let me start with the following. Let A be a matrix. And what I want to do is I want to write, this will save us some time. So what I have here is A is a matrix, but what I've done is specified that the columns, the vectors that are the columns, I'm calling them A1 through AN, so this will be helpful. With the little arrows above them, you can tell that they're vertical vectors so that they represent the columns. So in this particular situation here, I have N columns to that matrix. So each as I mentioned, each AO is a column vector. And I'm going to let X be a vector in Rn. Then what I'm going to do is define the product of AX. When I say we define, that means that there's no need to prove anything. Definition means this is how it is, and we're going to use this definition to prove other things. So when I multiply AX, it'll look like this. And then what you're going to do is take each of the entries in the vector and multiply it by a column. And you can see then, I'm going to then use all the n entries in the vector because I have n columns. So in particular, this multiplication will require that the number of columns that I have for A matches the number of entries that I have in the vector. So this is the definition of multiplication. We're going to extend it to matrix multiplication, but for now, we're just going to do a matrix times a vector. So if I do something like this, it's got two columns. That means I will be able to multiply it to a vector so long as that vector has exactly two entries. And so this equals, I'm going to take the 5 times the first vector, and then minus 2 times the second vector. And then you can finish it off to get the completed answer. Let me see, I have 5, 10, 15 minus 8, 10, 12. And so I have negative 3, 0, 3. Notice the size of the answer. This thing in the end is in R3. And that thing matches, well, what does it match? It matches the size of these column vectors. So whatever you happen to do, whatever you end up with is, well, you can see it's going to be the size of these column vectors because right here we're just multiplying these column vectors by a scalar. Now here I have a 1 by 3 matrix, and I'm going to multiply it to a vector. And so we will get 7 times block 1 plus 8 times block 2 plus 9 times block 3. Now when you see a block number, that's no different than just a number. It's a 1 by 1 matrix is nothing more than a scalar. So that's 7 times 1 plus 8 times 2 plus 9 times 3. And we get 7, 16, 20, 30, 50 for our answer. Or if you want to put brackets around it, you can. Now this multiplication is defined because I have 4 columns in my matrix and I have 4 entries in the vector. And then let me go ahead and finish it off. First, I'll do the multiplications. I'm doing them as quickly as I can so that you can use these for examples. But then doing quickly means that I am more prone to mistakes. And then finally we can add all the vectors together. So in particular, notice that the vectors that I originally had had 2 entries. Notice that my answer has 2 entries. So let's see, -8 minus 3, -11 plus 14 is 3. And then I have 10, 9 plus 28 is 37. Now, as a final example, I suppose this isn't something that's very difficult, but if I try to do something like this, I can't, because the number of columns in the matrix on the left only has 1, or there's only 1 column, and I need 3 columns so that would match the vector on the right. So this is not defined. So we can't even do it. All right, my next example switches gears a little bit. I want to create an equation AX equals B and solve. And what do we have? A is a matrix. I think it's 3 by 3, so we have 1, -3, 0, 2, -1, 5, 1, 2, 3, and then B. Remember, since B is an answer, it's going to have 3 entries because it'll match the number of entries that are in each column vector. So B will equal 0, 1, 1. And so we wanted to create an AX equals B. So let's do AX equals B will look something like this. Since we have 3 columns, 1, 2, 3, whatever vector I multiply it by has to have 3 entries. So X will have to have 3 entries. So let's go ahead and do that. So what I'll do is I'll let X equal X1, X2, X3. And so this equation then, let me go ahead and write it. There's my A. 1, -3, 0. 2, -1, 5, 1, 2, 3 times x1, x2, x3. And that equals b was 0, 1, 1. Now from here you can break the left side up if you want to, but what it amounts to is this. This I can immediately go to the following. So I'm making this video or this particular example to show you that you can go and make it into a vector equation and then assemble it and reassemble it back into an augmented matrix, or you can immediately go right into an augmented matrix. It'll save you a lot of time. And then when I find my answer, will be x1, x2, and x3. And we'll do the normal stuff that we do to this. First of all, I'll take out that negative 3 in the first column. I didn't touch row 3, so I'm going to put it in. And now let's see what we have here. 3 times 2 is 6, minus 1 is 5. Oh, let me put my 0 here. Then we have 3 times 1 is 3, plus 2 is 5. And then 0 plus 1 is 1. And now I will take the negative of R2 and add it to R3. Okay, now I've already got the answer for x3. I know that x3 equals 0. What I'm going to do is divide out that negative 2. So I'll do negative 1/2 R3. These are I usually do things like this when I know that I'm pretty much at the last step. And also, dividing the other side by into 0 doesn't change anything at all. Alright, now I'll use that 1 down in the bottom right corner to wipe out. Well, do I need to? Yeah, I'll go ahead and wipe them out. So I'll do negative R3 plus R1, and then negative 5 R3 plus R2. And of course there is a 0 in there, so I didn't change anything over. Oops, I made a mistake there though. I'll put that line in. So I have 0, 1, 0 still here. And well, I can see what R2. I made a mistake. I didn't make a mistake actually. What I did is I didn't use the second row to wipe out the thing above it before. Well, with that in mind, I'll divide by 1/5 and then I'll go ahead and take care of it. So I'll do 1/5 R2. You know what, now I think about it, I'm going to do a little efficiency here. Let's do negative 2/5 R2 plus R1. And that way I'll take that out, and that was premature. Negative 2/5 times 1 will put a negative 2/5 here. And now I can find my answer. I'm not going to bother dividing by the 5. I now know what I have. x1 is negative 2/5. x2 is 1/5. And our answer then is negative 2/5, 1/5, 0. Now next, let A A is another 3 by 3 matrix. Now we want to show that the equation AX equals B does not have a solution for all possible B, or all possible vectors B. And so what we'll do is, since it says show, that means what I'm going to do is a proof. Set up the equation AX equals B. So like you have a normal equation, you would try to figure out the X value, right? Well, that's the same thing here. I'm going to try to figure out the X vector. So immediately, I'll pull down my matrix a little bit. I can immediately go into, well, actually, I'm not going to immediately do it just yet, because I think that since I've only done one example so far, let me do a second example to illustrate more appropriately what I'm doing here. I think it's probably a good idea to get it into this form. Remember, the answer vector, the B that is, has to have the same number of entries as the columns. We do need our X vector to have 3 entries because we have 3 columns. So everything matches up. Let's go ahead and go into the augmented matrix. And let's see what happens. So we want to show that we don't always have an answer. That means we got to show something weird about the B's in the end. Well, let's see what happens then. Let me go ahead and wipe out the -3 and the 5 that occur in the first column. So I'll do 3R1 plus R2. Let me do that first. And then for the second column, I know I got that. Let's take a look. 3 times -3 is -9, plus 2 is -7. And then I have -12 plus 6 will be -6. Then I have 3B1 plus B2. Now let me target this 5 down here. So -5 times -3 is 15, minus 1 will be 14. And then -5 times -4 is 20, minus 8 is 12. And then finally we have -5B1 plus B3. And now I can see what's going to happen next. I don't need to completely solve this thing to figure out what's going to happen. I'm going to immediately use this -7 to wipe out this 14, but I think you're going to see that this -6 will also wipe out the 12. All I have to do for that is 2R2 plus R3. All right, let's see what happens in the final spot here. 2 times 3B1 will be 6B1 minus 5B1 will just be a B1. Then I have 2B2. There's nothing to match it with in the spot, so 2B2. And then finally the B3 was still there. So clearly we will not have a solution. If that last entry is not equal to 0. Now, describe the set of B for which there is a solution. Well, let's come back up to this final answer here. I know I may have a solution if this entry is 0. Does that guarantee us to have a solution? Well, yes, because what we have is a pivot here, right? And then this guy is a pivot. You can use it to wipe out the entry above it. So we would have a pivot in the only 2 non-zero rows that we need to have pivots. Nothing down here. So what we could do then is we would have a solution only if this is equal to 0. By the way, that reminds me, if this stuff down here is not equal to 0, you could use it to wipe out the entries above. So that's another reason that you can see why there wouldn't be an answer. If you have a pivot position in the answer column, then that can be used to wipe out the rest of the answer column. So there won't. So I think we had a problem that said that you'll have a solution if and only if there is not a pivot in the answer column. And I think this bears that out. So anyways, what is the solution? When do we have a solution? Well, we have solutions for this. We call it S. This will be our solution set, or I'll just write solution set. So the solution set of all those B's looks like this. We'll call it B1, B2, B3, such that B1 plus 2B2 plus B3 equals 0. For our next example, we have a 4x4 matrix. So A will equal, let's see, we have 1, 0, 1, negative 2, 3, 1, 2, negative 8, negative 2, 1, negative 3, 2, and then finally 2, negative 5, 7, negative 1. Question is this: do the columns of A span R4? That's the question that we have. That means, can we find let's call them scalars. And to stick with the notation that I would like to use, let's use x1, x2, x3, x4, such that, so we'd have x1 times the first column, and then we have plus x2 times the second column. And then we have x3 times the third column. And then we have an x4 times the fourth column. And let me put this equals, and I'm going to, over here, let's call this y1, y2, y3, y4. So, can we find scalars such that this equation is true for any choice of y, which is that y vector, in R4. So if I have a solution every single time, then I know that it spans them. But this whole expanded format here, I can rewrite this equation up here in the following format. Remember how we define multiplication of a vector to a matrix. I can simply write this equation. I can rewrite AX, we'll call it, equals Y, where X is obvious. So I think I even mentioned what it was. X is going to be X1 through X4. Let me go ahead and put my matrix in. We had 1, 0, 1, negative 2, 3, 1, 2, negative 8, negative 2, 1, negative 3, 2. We have 2, negative 5, 7, negative 1. And the x vector, let me call it x1, x2, x3, x4. That's how we compactified this whole left side up here. And then that was equal to y1 through y4. Now we can go to the augmented matrix. And we're ready to start whittling down our our matrix. So let's go ahead, or performing row operations, whatever you want to call it. So I'm going to do negative R1 plus R2. So I have 1. I'm going to just rewrite the first row. And I made a mistake there. I just realized negative R1 plus R3. I'm not going to touch row 2 because it already has a 0 where I want it. But I am going to do R3, so take care of that. So negative 3 plus 2 is negative 1. Then we have 2 minus 3 is negative 1. And then we have negative 2 plus 7 is 5. Then we have negative y1 plus y3. And I'm not done yet. I'm going to take out this item also. So I'll do 2r1 plus r4. Let's see what happens then. I'll have 6 minus 8 will be negative 2. I'll have negative 4 plus 2 will be negative 2. And then I will have 4 minus 1 will be 3. And then I will have this side over here, 2r1, we have 2y1 plus y4. Like so. Now let me go ahead and move on to my next pivot, which is this guy right here, and start wiping out the entries above and below it. So it looks like I can do negative 3r2 plus r1. So negative 3 minus 2 will be negative 5. And then 15 plus 2 will be 17. And then we have negative 3y2 plus y1. I think I'll write it as y1 minus 3y2. I'll keep them in order. I think it'll prevent me from being confused. The second row I'm leaving alone. 0, 1, 1, negative 5, y2. And I'm also only going to go as far as I need to go before I can determine if there's an answer or not. Remember, we're asked to determine if these columns can span R4. So if I get to a situation where I know for a fact there's not a solution, then the answer is no. Now, I'm going to take this one and wipe that out simply by adding R2 plus R3. Looks like I get 3 zeros. That's not, oh, even more. And now if I take this plus this, I have negative y. What did I do? I took this plus that, negative y1 plus y2 plus y3. And then to take this out, we're going to have to do 2r2 plus r4. So that'll wipe this. That'll also wipe this, but unfortunately, for here I'll have negative 10 plus 3 will be negative 7. And then I'll have 2y2 plus this stuff. So 2y1 plus 2y2 plus y4. Now I'm close. However, I know that we will not have a solution when this row right here, when this item here is not equal to 0. So, for example, AX equals, let me see, what did I say here? Let's put, I said when these, so when this, we will not have a solution when that's not equal to 0. I said it right. Okay, I just wanted to make sure. Negative 1. So I could do like this and all these things. So if you look at it, this would be negative 1. Of course, that doesn't equal to 0. So this has no solution. So all I got to do is come up with any vector that satisfies these three things. And now that I mentioned, it had 4 entries, but I only had a description involving the first 3 entries. That's okay. I could put a 1 in the second spot, a 1 in the third spot. I could almost put anything that was not equal to 0, and I could probably put, it didn't even say anything down here, so I can even put anything in this spot. It didn't even talk about those things. So none of those will have a solution. Next, let's let, we're going to have U will equal 725. V will equal 313. And then W will equal 610. Now suppose we know the following. We have 3U minus 5V minus W is equal to the 0 vector. Find x1 and x2 scalars such that So see if we can find that. Well, what's interesting is what they gave us up here and is equal to the 0 vector. That's important. Notice that column 1 is this vector, column 2 is this vector, and the answer vector is this W over here. But we are given this information here. So basically what we have then is we have a matrix times xy, and this thing over here is W. But we already know that 3u minus 5 of e equals W. We already have that information. And that is W there. There's u and there's v. So we can change our matrix equation without actually doing any work. I have my x1 and x2. They're right here. The x1 will be attached to u, the first, and the x2 will be attached to the second column. And so we know what our answers could be. I could put a 3 for x1 and a negative 5 for x2, and so I've got an answer. So x1 equals 3, x2 equals negative 5. That brings us to a theorem. So this, let's see, we want A, let A be an M by N matrix the following statements are equivalent. I'll talk about this in a minute. For each vector B in Rm, Ax equals B has a solution. Each B in Rm is a linear combination of the columns of A. The columns of A span Rm. A has a pivot position in every row. So let me show you the basic idea on how you prove such a thing like this. The proof looks like this. I make the assumption that A is true, and from that I am going to imply that B is also true. So let's start with that, and I'll explain more of the details or the overall logic when I'm done with this thing. So we're going to assume Ax equals B has a solution for each B in Rm, for each vector B in Rm. So that's the assumption we make. Now we're going to use that to get at the second thing, which is part B. We're going to try to prove that part B. So what we do, start with Ax equals B has a solution. Well, if that's true, then we can rewrite that. If you'll remember, if x goes from x1 through xn. Let's take a look here. This A is m by n, so it has n columns. So we might look at it this way. So there's our A written as column vectors. And let me put my X. And B, I really don't even need to break it out just yet, because the way we multiply is defined in the following format. Well, that's exactly what it means for B to be a linear combination of the columns of A, because each of those A1 through AN are columns. And so I finished what I was trying to prove. I have proved part B. Now what we do is we move on and we do this. B implies C. So now we assume that part B is the true statement, and I want to now prove that part C is true. So let's see. We're going to assume for part B, now assume that for any vector B in Rm, there are scalars x1 up to x, oops, let me make that better, x1 up to xn, such that that is in fact what it means for B to be a linear combination of the columns of A. We can find such scalars to make that happen. Now part C tells us that the columns span. Well, that's pretty obvious. So this implies that B is in the span of A1 up to AN. Now, since we have a linear combination for every I wanted to emphasize that since we have a linear combination for every B in Rm, we have that the span of A1 up to AN does in fact equal Rm. Next, we're then going to prove that C implies D. So now assume the columns of A span Rm. So for any B in Rm, B is in the span of A1 up to AN. I didn't really say anything new, I just wanted to remind you. So pick any b and find x1 up to xn in R such that and then what we're going to do is I can immediately go to this kind of a look to it. So I'm looking at A in terms as columns, and then I'll put my B over here on the other side of the augment. Of course, the x1 through xn is some vector, but it doesn't appear when you write the augmented matrix. Or another way you can look at this is just for a simple purpose right now, is I could, instead of have all those columns over there, I could instead write this. And so what we're going to do then is, this is to keep notation simple as we can. Run through the row operations to get. So I'll start with A/B, and then I'll do row operations, however many I need, until I end up at something like this. And U is in echelon form. So that's a matrix in echelon form. I know I can always get there. So we've got to think about that echelon form carefully as we're going to do this next step. Some of these are a little complicated and nuanced, so pay attention. Now, since we have a solution, we cannot have something like, you can't end up with something like this. Well, I don't know. Let me see if I can do this. So let me think, this will be like the bottom of a matrix, but it's the rest of the matrix is above it, so I don't really want to say anything up there. But when we get U to be an echelon form, remember, you could end up with rows of 0. So what we don't want to happen is that we don't want the rest of these items to be non-zero, because then we don't have a solution. So we know, since there is a solution, since we have a solution, we cannot have something like this unless dk equals 0, dk plus 1 equals 0, until we get to dm. And I realize here, I forgot we had m rows. But we can create a D that is D equals 0, 0, dot, 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 0, but a 1 in the last spot. So that if we were to have a row of zeros in U, we could have a D here. What I'm getting at is that U slash that particular D, we know has no solution. We could reverse all of those old row operations and take us back to, I'm going to call this one B star, because it may not be the same B that I started with. I know there's a solution, but what I'm getting at is this. We could take and reverse the row operations to get back to A. I know I can do that. Then this B star star is in RM is not is such that AX equals B star has no solution. This is a contradiction. We know that we're supposed to have a solution no matter what the B was. So that means that U cannot have rows of 0. If that, well, now U is in echelon forms, that means that it goes and it works its way downward, moving to the right. Remember, the echelon form, we may not care about what happens above the diagonal entries, but below the diagonal entries are always 0, or as diagonal as we can get. So you cannot have rows of zeros. That means that A cannot have, under the row operations, A could not have gotten to U if you were to have those rows of 0. So U cannot have rows of 0. And if our echelon form does not have rows of 0, then it must have the first entry of each row of U is a pivot. But there's the same number of rows in U as there are in A. But these are the same pivot positions as in A. Thus, A has a pivot in every row. I'm almost done with this theorem. I know by now you might be falling asleep, but now I'm going to assume that D is true and prove that part A was true. So let's make the assumption. So now assume A has a pivot in every row. Now, what was A again? Once again, do the row ops. Where U is in echelon form. Also, let B be any vector in Rm. Now, once again, I'm going to work the same kind of thing. Suppose, I'll show you in a second about, suppose that AX equals B does not have a solution. So we can do the same things before. We can do A, B, U, D. So since we know that the equation does not have a solution, this would imply that U would have a row of zeros, at least one, but the corresponding entry in D is not 0. So the only way we don't have a solution is when we have something like this. And then you would have to have, I don't know, let's call it D sub k like I had before. Well, we know that this cannot happen because this would mean that U, remember this is supposed to be in U, that would mean that row has a U of zeros, which means that it could not have a pivot in that row. That implies U does not have a pivot. In that row. So I've reached a contradiction. What that means is I made an assumption somewhere here that was not true. What was the assumption? The assumption was that this does not have a solution. So therefore, AX equals B has a solution. That finishes the proof. Now look what we did here. The proof followed these features. We proved that A implies B, which implies C, which implies D, which back again implied A. This means that they're all equivalent to each other. Because when you look at it, when you prove two things are equivalent, this is the stuff I was talking about, if and only if. A, if I assume that A is true, I can get to B. Now think about this for a minute. If I assume B is true, then I'll be able to prove C is true, which proves D is true, which then I'll be able to prove A is true. So if I assume B is true, I'll be able to prove that A is true. If I assume A is true, I'll be able to prove that B is true. What we get then is from this, I will get that A is equivalent to B. I can do it for all the letters. If I assume A is true, I can show that C is true. If I assume that C is true, I'll be able to show that A is true. And so I will be able to get this equivalence. I'll be able to do A is equivalent to D. I can keep going. B is equivalent to C. B is equivalent to D. And then finally, C. So I already took care of B to A, right? C is equivalent to D. And I need to make my arrows double. So that means that A is true if and only if B is true. If and only if C is true. Well, you get the idea. So that's what it means for all of those things to be equivalent, is that kind of logic. Let's do an example. Can a set of 3 vectors in R4 span all of R4? So let's take a look. We want 3 vectors. Let's create a matrix with those 3 vectors. And we're in R4, so x1, x2, x3, x4, y1, y2, y3, y4, z1, z2, z3, z4. So I have 3 vectors in R4. I've decided to make a matrix out of them. So notice that we have more rows than we have columns. Well, if I do the row operations, in an effort to get an echelon form, so in order to get an echelon form, I start running them. Here's what I'm going to end up with. Let's call it U like I did in the theorem. we could get a block maybe in that first corner, but there's no guarantee that I'll be able to get it to it. Now for my next pivot, and remember I'll get zeros underneath of it. For my next pivot, it has to be in the next row. And in fact, I'm being a little lazy here because I forgot that I'm actually dealing with a real matrix here. The next one could be in the next row, in the second column, the third column. It could be in any of the 4 columns, but the best I can do is this. Maybe there's stuff above, I don't care. Then I have to go down and to the right again, maybe to the right more than one step. But guess what? I'm done because I've only got 3 columns. This is as far as I can get. Seems we've run out of columns. So, in a situation like this, no. The answer is no to that question. No. They don't span R4 because they don't have a pivot in every row. Generalize. So that's the answer to that question was no. Suppose, generalize. Suppose we have n vectors in Rm where n is less than m. So that's a situation where, once again, well, it depends. I didn't, and A is an M, and A is an M by N matrix. So I have, as before, more rows than I have columns. So the same thing as before. Here's my A that I'll start with. Let's call them all A. A11, A21, dot, dot, dot. A, what is it? Is an M by N matrix, so M rows and N columns. So there's that. And then I'll finish it off here. Then we have A1N, A2N, all the way down to AMN. And then we'll go ahead and run through it. The row operations, that is. And once again, the best we're going to be able to do is this. And now I don't know exactly how much, but I know I'll get zeros through the rest of the thing. I may have multiple rows of zeros down here, so I don't know how many there could possibly be, but I'll have things like that. And once again, it's going to violate the same things because we only have n rows, but we have m rows, but we have n columns, and there's not enough columns. I need an extra, however many zeros there are here. That's how many extra columns I need to even have a shot at having such a solution. So the same thing, we cannot have a set of n vectors in Rm cannot span Rm if n is less than m. We need more vectors. Let's consider A1 equals 1, 2, 3, and A2 equals 4, 5, 6. Both of these things, of course, are in R3. I've only got 2 vectors. I cannot possibly go and span R3 with only these 2 vectors, but I do want to show you some things. I'm going to make up A will equal 1, 2, 3, 4, 5, 6. And let me go ahead and whittle it down using the row operations. I don't want a lot of them. I just want to get to a certain point and then I'll stop. Negative 2 times 4 is negative 8 plus 5 is negative 3. Of course, this will be the same. And negative 3 times this will be negative 12 plus 6 will be negative 6. And then I will do negative 2R2 plus R3. Like so. So you can see there's a row of zeros. My echelon form is not as perfect that I would like to have it. Now, pick D equal to 0, 0, 1. So, UD, if I call this last matrix UD, this one here, or just U, this form will look like the following. So I know I can manufacture a vector that's not a solution to the echelon form. But remember, all of these things are reversible. So the first thing I'm going to do is reverse R2 and R3. So we will do, remember, if you remember how to do this, all you've got to do, instead of do negative 2R2 plus R3, I do positive 2R2 plus R3. This will reverse the last step that I went from U, from A to U. So I'm going to reverse that last step. And you'll see the matrix A coming together as I do all this stuff. So 2R2 plus R3. And now I'll go ahead and reverse these other two. So I'll do 2R1 plus R2 and I'll do 3R1 plus R3. So when I do that, 2R1 plus R2, I will have a 2 here and a 5 here and a 0 here. And then 3R3 plus R3, 3R1 plus R3, I'll have a 3 here, a 6 here, and a 1 here. So what does that mean? So now it's a B. So this is an A, and now it's a B. So that's a starting one. So AX equals B has no solution. So that's the beautiful thing about the U, the echelon form. You can create a non-solution in the echelon form and then run the row operations in reverse to get a non-solution to the original equation. If A is an M by N matrix, U, V are in R to the N, the number of columns, because I'm going to end up multiplying them. Then A times U plus V is the same as AU plus AV. If C is a scalar, then A times CU equals C times AU. So I can pass the C inside and outside as I want. Now the proof of this, I'm really not going to do a lot. You can run through this yourself. But you can let u, for instance, equal u1 up to un, because it's got to have n entries. And then when you run the multiplication through, well, let me set a first. You can do a equals, well, you know, I don't think you need to go this far with it. Let's just do a equals, and A is an m by n matrix, so we have n columns, like so. And then when I do A times U plus V, that'll be A times, and then I'll be able to put my vectors in here. And then you can use the addition property of vectors. And then remember, if I rewrote the A like the following, then the rule that we use to multiply out this thing looks like the following: u1 plus v1 times a1 plus un plus vn times an. I just need to be careful where my arrows are and where they aren't. That's the thing that gets me the most. You got to remember when you're dealing with vectors and just scalars. Of course, you can use the distributive property that we had for scalars over vectors. And then you can rearrange, because everything's commutative in this world. And this is exactly what I was talking about here. You see how that little thing appeared above the V? I did not mean to put that because that V was a scalar. And so then this right here on the left is the definition of multiplying a matrix by a vector. And the other one's the same way. And that proves the first part of the theorem. On the other hand, when you try to do something like this, that'll be A times, remember, C times U, you multiply C to every item in U. Like so. But then I would once again imagine my A to be in this form. And then I can use my rule for multiplication. Like so. But then you remember there was one of the theorems we had earlier that said there was sort of an associativity with these things that look like this. I could instead do C times U1 A1 plus C times UN AN. So that was a form of associativity. I could then factor the C from everything. And then I can reassemble my matrix. And that shows the second part of that theorem. One thing I don't think I mentioned here was the following. If you have a scalar times a vector, you don't have to worry which side the scalar is on. You get the same thing if you reverse it the other way. So don't let that bother you. C is a scalar, and then U is in some Rn. Before I leave this rather long video, one last thing, and this is called the row vector rule. For multiplication. It's a shortcut to what we had before. If I want to do, I think the best thing to do is just with an example. Let me do 1, 2, 3, 4, 5, 6, 7, 8, 9, x1, x2, x3. You can check the details out, but it works like this. What I do, and this is the way that you probably are used to it if you've ever seen this stuff before, I take this first row and I multiply it along these things. So when I do that, that means I match the 1 with x1, and so I'll get x1, and then I'll match the 4 with x2, and I'll add those. And then I'll match the 7 with x3. Like so. Then I'll move on to the next row, 2, 5, 8 times that again. So I have 2x1 plus 5x2 plus 8x3. And then I'll move on to the third row, 3x1 plus 6x2 plus 9x3. And so that's a much faster way than multiplying it all up. But you can see that it actually does work out that way. x1 times 1, 2, 3 is represented right there. x2 times 4, 5, 6 is right there. And then x3 times 7, 8, 9 is right there. So you can see it's reformulating and looking at these things in different ways will provide us with powerful tools to be able to prove results later on in the course.